So we will also consider, given a scheme X, we will consider small étale site. Small, I could consider FPQC, but let's say étale site of X. And this is the name for this. It's X étale. So objects here, the category, are schemes étale over X. Covers, topology is given by topology defined by étale covers. Alternatively, I can consider what's called big étale site over X. And the name for this is schemes over X equipped with étale topology. So here C is the category of all schemes over X, and covers topology is given by étale covers of Y in schemes over X. And there are variants of this. You can also consider small Zariski site. So here objects are just Zariski open subsets. Or you can consider big Zariski site. So this is just the category is the category of all schemes over X, and covers are given by Zariski covers of Y over X. Okay? That's notation. And now I want to discuss some further applications of faithfully flat descent. So first I introduce so let's talk about torsors. Torsors. Okay? So this is. Okay, so suppose we have any site, and let's say that G a sheaf of groups on C. I do not assume that my groups are abelian. So a torsor, a G torsor, is a sheaf of sets let's call it T, with an action of G. So meaning that we have a map from G hat times T to T, which is an action map. So for every object of C, this defines the action of X valued point of G on T of X. Such that locally T is isomorphic to G with its canonical action, such that which is locally isomorphic to G with canonical action. G times G to G, given my multiplication. So let's, as an exercise, just on this general notion of Grothendieck topology, let's spell it out what it means that it's locally isomorphic. So what does it mean? Покрытие. У нас есть понятие покрывающего решета. Покрытие чего?
Любого объекта.
So okay, locally means that for every object X, object of C, there exists a covariant sieve. Да.
Что локально изоморфно G?
Пара, состоящая из пучка множеств вместе с действием пучка групп.
И что значит, что как пучок множеств может быть изоморфен пучку групп?
G — это пучок групп, но в частности это пучок множеств, на котором G действует с помощью умножения.
То есть мы забываем.
Да. Ага. Правильный вопрос. Okay, so I want to spell it out what it means that it's locally isomorphic. So for every object, there exists a cover. There exists a covariant sieve on X. Let's say on X, such that so what should be true? What is the condition?
There exists a U locally given isomorphism from T to G.
Okay, so U locally given. Let me. I think this is not a correct definition. What you say? It would mean that you see the category of U locally given sheaves is equivalent to the category of sheaves, right, on any site. So any U locally given isomorphism is the same as a globally given isomorphism. So this condition is definitely too strong. Yes. So for every such that for every object U in object of this covariant sieve, so if I consider my pair, which consists of T together with action of G on T, right? So T is a sheaf on category C. In particular, it's a presheaf. Let's restrict it to category of objects over U. So what is this? This is a category whose objects are pairs, W mapping to U, and morphisms are over U. For any category, I can consider the category C over U. Что? А объекты что?
Объекты решета — это морфизм X.
Ну да. Значит, Ну, да, значит, U это...
В объекте этого...
Да. Ну, хорошо, я... Правильно. Он, конечно, отображается в X, но я как бы рассматриваю правильно. Хорошо. Спасибо. So this must be isomorphic to G with view it just as a sheaf on sheaf of sets on C with action of G given by multiplication restricted to C over U. Okay? This is a weaker condition than the one that Stepan suggested because, so imagine that we work with Zariski topology in Zariski side, and so our cover in SIF is generated by a cover, by just a Zariski cover of X. So U is disjoint union of two open sets that cover X. Then, so this condition says that if you take this T and restrict it to any sufficiently small open set, namely the one that contains in either of the two that cover, then so the restriction is isomorphic to the sort of trivial torsor. But this isomorphism, so we in particular, so if X is covered by U1 and U2, so we have a trivialization on U1, we have a trivialization on U2, but we do not require these trivializations to be compatible on the intersection, right? U local isomorphism would amount to, given a trivialization on U1, U2 plus compatibility on the intersection. Good. So that's a notion of torsor. So here is an example. Let's take an algebraic group. So I want to take consider the group scheme GLN. Say over, I think of this as a group scheme over spec Z. Well, so GLN exists over any field and even over spec Z. So what does it mean? So it's GLN, well, is an affine group scheme. So it's spectrum of the following ring. It's generated by matrix coefficients Aij with adjoint inverse of the determinant, right? So you take polynomials in n squared plus 1 variables and add one relation, that the determinant of this matrix is, that this variable and you localize it with respect to the determinant, okay. So this is a group scheme. The product of matrices defines a co-multiplication, the Hopf algebra, Hopf ring structure here, right? So good. And then, so using the theorem that, the last theorem from the yesterday's lecture, we conclude that so let's consider so this is a group scheme, and let's consider the sheaf of groups represented by this group scheme. So namely, so for every x we define sections of this guy over x to be all morphisms from x to GLN. View it as a group, view it as a scheme. This has a group structure given by the multiplication on GLN. So if you wish, that's the same as just matrices, invertible matrices, with coefficients in global functions on X. Right? By definition. So given a morphism from X to an affine scheme is the same as given a map from this ring to functions on X. And this gives you a matrix, invertible matrix. So, and then by the theorem that we proved actually last time, this is a sheaf in this is a sheaf on big FPQC side of all schemes, FPQC. So I could put here spec Z if you wish. So what the theorem that I stated last time was that for any scheme, the functor that takes X to morphism from X to this scheme, it's a presheaf of sets. It's actually a sheaf for FPQC topology. We have descent for FPQC covers. I didn't prove that theorem in general, but I proved it for affine schemes. And this is a affine scheme. Okay? So, so now theorem, which is again application of faithfully flat descent, is that GLN torsors Okay, so I want to describe this in terms of something familiar to everyone. What is it? On X, on schemes X, F, P, Q, C. So what is this? I claim that this is the same as vector bundles. In the usual sense, locally trivial for the risky topology. Bundles over X of rank n. So this is also equivalent. Для чего?
Нет, можно сразу сказать, что торсоры классифицируются гомологией, и тогда в случае GLN
ну да, но только здесь они классифицируются как гомологиями, об этом мы сейчас поговорим еще, но они классифицируются как гомологиями с коэффициенты вот в этой топологии. А здесь речь идет о векторных рассвоениях в топологии Зарисского. Они локально тривиальны в топологии Зарисского. Поэтому вот в этом как бы главное содержание.
Справа имеется в виду...
Yes.
Справа что-то вот на маленьком Зарисском сайте.
Да. Да. Okay. Yes. So this is also the same as so the statement here really consists of two parts. So one part is I think it's also familiar to everyone. So that's the same as GLN torsors on X Zariski, right? This is almost a trivial statement that vector bundles are the same as Zariski locally trivial GLN torsors on the small Zariski side. And this is also equivalent to GLN torsors on X et al. Okay? So one kind of statement, one sort of really the essence of this theorem is that if you consider a GLN torsor, which is here, then there exists an open cover of X, Zariski open cover of X by open subsets of X, such that the restriction of my torsor to any open subset is trivial, which is really a non-trivial statement, and it's not true if you consider GLN, say, replace GLN by, say, orthogonal group or projective linear group, PGLN. Okay? So let's prove this. Proof. So I will give a construction. I will prove this statement. And you will see that along the way we will prove the other two, which is kind of easier. And we will use this a lot. So let's let's start by so in this proof it will be based on the, well, one ingredient is the following trivial observation that for any ring, commutative ring R, the two categories are equivalent. GLN R torsors. Here I consider, what I mean here is just torsors of points. So I consider sets with simple transitive action of this group. So any such torsor is isomorphic to GLNR itself with action given by multiplication. But this isomorphism is not canonical. And so I claim that this is the same as free R modules of rank R, n. Okay? So both categories have the same, well, one isomorphism class of objects. Any two objects here and here are isomorphic. Here it's every object is isomorphic to Rn. So, but this have non-trivial, well, I consider this as really as groupoids, right? So groupoids, this I discard groupoids. So groupoids means that I consider only isomorphism between torsors. I don't know actually what is, well, there's definitely, this is also groupoids, groupoid. So every object here is by definition an isomorphism. And of course, you can consider morphism between R modules which are not isomorphic. I discard them. This is an equivalence of groupoids. And well, one way of proving this would be to say that since any object here is isomorphic to Rn, it suffices to, and every object here is isomorphic to the trivial torsor, it suffices to compare automorphism group. Automorphism of Rn is by definition GLNR. Automorphism of the trivial torsor, right? So this set with the left action of GLNR is also GLNR, where the GLNR acts on the right. So you have one object, and the group of isomorphism, automorphism of these objects are the same. But I really want to kind of construct the functors in two directions. So let's see how it works. So suppose you have a torsor T. So what you do? So this is GLN torsor. So what you can map it to T. So this is notation. So I have a torsor and I have a set on which group GLNR acts. Then I can kind of take the twist. I can twist the RA module by a torsor. And I will explain what it means. This is notation. This is the following. You take the Cartesian product and now this has a diagonal action of GLNR. So GLNR acts here and it also acts here. And I mod it out by the diagonal action. Now every element here can be written as every element here can be written. So if you fix an element A, then every element in this quotient can be uniquely written as A times X, where X belongs to Rn.
Это то же самое, что коядро действия.
Коядро. А что значит коядро действия? Какого? Ну, я беру множество орбит на каком-то... У меня группа действует на множестве, я беру множество орбит. Okay, so I want to say that this has a structure of a group, and in fact of an R module. So how you define the group structure? You, if you have two elements here, you can always find, so fix any element A of T, then any element in this quotient can be uniquely written as A, X, where X is here. And then A, X plus A, Y is equal to A, X plus Y. So that's how you add elements here. So I claim that it's well defined, it's independent of the choice of A. Okay, and similarly you define multiplication. So this is definitely an R module, and it's once you fix A, T here, it becomes isomorphic. This choice of A defines an isomorphism of this module with Rn. So it's free of rank n. Okay. Now let's construct a map in the other direction. So suppose you have это функтор отсюда сюда.
Как бы не очень содержательно, потому что любой функтор будет эквивалентностью.
Ну да. So this is my E. And now conversely, if I have E, but I really will use this construction in the proof in general. I will glue this kind of. So suppose I have a free module over R. So how to construct a torsor? Well, I look at all isomorphisms of R modules between Rn and E. So I say the E is free, so it has a basis, consists of n elements, and this is the set of all bases in my E. And so GLN R acts here by its action on Rn. Okay, these are two mutually inverse functors. Okay, so now let's go back to the proof. Ага.
То есть мы откуда куда? Мы из вектор банда.
Сначала мы по торсору построили модули, и наоборот.
А мы типа сейчас только для эфирного случая.
Нет, сейчас мы в общем случае все сделаем.
Ну сейчас распределяют.
Да. Сейчас вообще были торсеры, они как бы на точке, они тривиальны. А вот сейчас у нас будут нетривиальные торсеры. Мы эту конструкцию склеим, используя теорему о плоском спуске. Okay. So let's do it in general. So first, I'm proving this first equivalence, right? Vector bundles and torsors. So again, this is an equivalence of two groupoids. I discard all non-isomorphisms here. So this is an easy part. From vector bundles on X to G-line torsors. So if I have E, vector bundle, and I think of vector bundle as a locally free sheaf for the risky topology over X. Then, I need to tell you what is T. I need to define a torsor. So I need to define a torsor, a sheaf of sets here. So T of X of Y over X. This is F. This is an object here. And okay. So what can I do? I'll just take all isomorphisms between in the category of OY modules between OY to the n and F upper star E. Okay? So E is a vector bundle, locally free sheaf on X. So its pullback is a locally free sheaf. It's a vector bundle on Y. And I take its all trivializations on Y. And this gives me a torsor under GLN. Нет, почему? Это пучок. So I claim that, so first of all, this GLN Y acts here because it acts here. And I claim that it's a sheaf. So T is a sheaf on F schemes X FPQC. So let's see why it's a sheaf. So this follows from another result that we proved last time, that if we take any quasi-coherent sheaf, well, it's a corollary of the main descent theorem. If you take any quasi-coherent sheaf on X, and so it follows from the following fact that for any E in quasi-coherent sheaf on X, the functor that assigns to Y over X global sections and Y F upper star of E is a sheaf, F P Q C sheaf, right? So why that? Well, so that's this we discussed last time, and.
Никакого отношения не имеет. Ну, то есть вот если у вас y это x, просто
тождественно. У вас какое-то нетривиальное расслоение на иксе.
Да.
Но у вас нет ни одного изоморфизма.
Нету. И что?
В каком смысле это?
Ну, в смысле, множество будет пустое. Сечение на y, глобальное сечение моего-то. Okay? Yeah. So now what is how to see that T is a sheaf? So what is a section? Section of T. So this is a collection of n global sections of this guy. So this is a homomorphism from OY to the n to this guy, together with a collection of n sections of the dual vector bundle, such that so you have O n y mapping to F upper star E, together with a map from this guy to OYN, such that the composition is isomorphism. Okay? So, and we know that sections of this guy, global sections, form a FPQC sheaf. So you can descend them along FPQC covers, and therefore these maps, which is just collection of n sections, you can also descend them. Okay, good. And of course, if E is trivial, so if I choose, so I need to show that my torsor is indeed locally trivial. So this category, so remember that, so this category, I need to show that it's a torsor here. This category has a final object, namely X. So saying that a sheaf of sets with action of G is a torsor here, well, it's is equivalent to saying that X has a FPQC cover such that the restriction of my torsor to any open set in this FPQC cover is trivial. But I can just take for X, for my cover as a risky open cover where my vector bundle is trivial. Right? Is it agree? Or, good. Now, this is an easy part. Well, still we use descent, but only a small part of this, of the theorem that we proved. Now, okay, so now I want to prove it in general. So the inverse direction. So so here is what we will do. Okay, so now we have a torsor, T. So choose a covering sieve. Sieve. Да, в другую, значит, по торсеру, да, спасибо. A covering sieve of on X. Covering sieve, let's call it U, such that T, such that for every U in here, the restriction of my torsor to schemes over U is isomorphic to G line. view it as a torsor on schemes over U. So this exists by definition of a torsor. Now, for U again in here, define a vector bundle EU. This will be a vector bundle on this scheme U, and this is just TU. Right? So I know that this torsor, this set, is non-empty. That's my assumption. So saying that we have this, in particular, it means that, well, saying that we choose, well, so for every U here, this is, T of U is non-empty. That follows from this assumption. And I twist this torsor by, so here I have action of GL n of U by, and I take the trivial vector bundle, ON U. So I take the trivial vector bundle and I twist it by a torsor. Non-canonically, this vector bundle is this is a vector bundle on U. Vector bundle on over U. This is a trivial vector bundle because once I have an element here, once I choose an element here, it gets identified with ON, right? By construction. But it's not canonically trivialized because this trivialization depends on the choice of an element here. So what we constructed, so what we produced, so for every object U, we produced a vector bundle over U. Vector bundle EU. So this gives a so the collection of all this EU gives me an object in the category of quasi-coherent sheaves, locally given quasi-coherent sheaves on this sieve. So what do I mean here? So what is a locally given quasi-coherent sheaf? So for every U here, I am supposed to give a quasi-coherent sheaf on U, so this vector bundle. And for every morphism, W mapping to U, I'm supposed to give you a map, an isomorphism between F U and F upper star of E W, right? And I claim that indeed, this morphism here is induced by the map from T of U to T of W. Что? Да, что-то здесь не так. Правильно. U. Okay? So if I have a section of my torsor over U, I can pull it back to W, so I get this map. And this gives me a map. This produces me a map in this direction. Which is an isomorphism. Okay? So, so this defines a quasi-coherent U locally given sheaf. And by our descent theorem, this is the same as quasi-coherent sheaf on X. So now, along the proof of this faithfully flat descent, so we proved there was a lemma, and the second part of the lemma was that the property of a module being locally free of finite rank is preserved under faithfully flat best change, which means that this equivalence takes locally free modules of finite rank to locally free modules of finite rank. So we get a quasi-coherent sheaf here, but in fact, because every guy here is locally free of finite rank, this quasi-coherent sheaf on X will be locally free of finite rank. So this gives E. Gives E. Okay? That's the argument.
But why this E does not depend on the choice of the covering seed in this generalization?
Oh, well, because for any two covers, you can consider it, their intersection, right? So covering sieves form a filtered system. So if you have two covers, choose a smaller one, finer one.
So you claim that faithfully flat descent is transitive.
Yes, yes. Because it's obvious that the functor from here to here, which is the pullback functor, is transitive. And since it's an equivalence, the inverse functor also must be transitive. Okay? Yes.
So there is a characterization of a scheme that a scheme is a sheaf on the category of schemes which is locally represented, right? It is a risky topology.
Locally representable. Okay.
And it seems that in this theorem we're sort of trying to extend the notion of vector bundles to the following objects. That if you have a functor on the category of schemes which is locally represented in the FP.
Why it's locally? It's even globally representable.
So, I mean, our discussion here makes sense for the following object. If we have a functor from the category of schemes to sets, which is locally representable in FPQC topology. So is there a name for such objects?
Okay, so you want to, so we discussed how to descend sheaves, quasi-coherent sheaves for FPQC topology. We discussed how you can descend morphisms for FPQC topology. And now you want to descend schemes for FPQC topology. Am I right?
Yeah, I want to.
Okay, so that's what I'm going to talk about now. But this is more delicate. It doesn't work in general. It works only for quasi-projective schemes. But I will prove it only for affine schemes. Да.
Открытое множество.
Да.
Отображение открытого множества выцветано нейтрально.
Какое отображение?
Ну,
Да.
открытое подмножество x отражается нейтрально. Да?
Почему этально?
Нейтрально.
Ну, это изоморфизм.
Это изоморфизм. Что такое этальное отображение? Ну, да, есть. Угу. Неконечное этально. Okay. So here is another point of view on torsors. Yes, so to here. Let's say geometric torsors. torsors. So suppose we have a group scheme, a flat group scheme say of finite type. It suffices to be finitely presentable, but finite finitely presentable over some base. So if base is Noetherian, that's equivalent to saying it's a finite type. So think of GLN, for example. So definition, a G torsor, well, geometric G torsor, is over S is a scheme X over S with an action of G. What is an action of G? It's a map from G times X. So G is a scheme over S, X is a scheme over S. So I take the fiber product over X over S to X, which is an action, right? So associativity holds. Such that two conditions hold. So one condition is that this map F is FPQC cover. And the second condition is that the map from G times X over S to X times X, given by the formula G comma X goes to X comma GX, is an isomorphism. Okay, so well, a comment on this. Suppose you have a finite set with an action of a discrete group G. Then this condition is equivalent to saying that the action of G on X is simple and transitive. This. Right? So in particular, well, if I take any point, so if I pick a point, say a K point with value in the field of X, and look at the fiber of F over its image, then this has an action of K points of G, and this action is simple and transitive. So this explains the terminology, right? So is it clear?
If you demand that F is FPQC covered, then you should demand that G itself is G to S is also surjective, right? Otherwise you don't have.
Yes, otherwise it's empty.
But if you have
Well, but it's surjective just because it has it's surjective because it has unit. identity element. Every scheme, every group scheme has identity element.
And if you have like a fine line with double origin over say fine line, this is okay.
Yes. Yeah, unless I'm not sure that this is a group. Is it a group scheme? No, I don't think so.
The double origin is just Z mod 2Z.
I'm not. I doubt that you can. First of all, it's not flat.
Like it's like locally isomorphism.
Really? I thought that.
You take A1 with doubled origin and map it to A1. This is locally isomorphism on source.
Okay. No, I understand that it's locally isomorphic on source, but not on the target. So the direct image of the structure sheaf will not be a vector bundle, probably. Will it?
Flat. Wait.
Typically, for flat finite morphism, the number of points in every fiber is the same.
Wait, is the definition of flat not you take a point and the local ring?
Yeah, you're absolutely, let's see. So you're saying that it's flat, right? Yeah, you're absolutely right. It's a flat. It's a flat, and what is the direct image of the structure sheaf? Probably it's the structure sheaf, right?
Yeah, because any function of the
Yes.
Yeah.
But I don't know whether it's a group scheme actually. I thought that you can check that if you have a group scheme over a field.
It's not over a field, it's over every.
Yeah, over a field it must be separated.
Yeah, no, it's over A1.
Maybe, but well, one has to check that it's okay. So isomorphism. Now, да.
Связаны эти geometric tools с прошлым.
Да. Вот в этом собственно, и
Просто
теорема.
Сейчас, а вот вопрос, вот мы когда ЖЛН рассматривали, то что-то было не то же самое, что мы сейчас определили, что-то другое.
Ну, там, строго говоря, там у нас был пучок, а здесь у нас схема.
Ну, как бы схема является пучком, поэтому
Да,
геометрический частный случай тоже.
Ага. Представимый. Любая групповая схема определяет пучок групп.
Схема определяет пучок.
Да.
Схема пучок.
Ага.
Собственно, это что, в общем, тут доказывает, что схема это
So suppose you have G. So G is a group scheme over S. Then I can define a sheaf represented by this G. To be just morphisms over S from X to G, right? So given a group scheme, I can construct a sheaf for FPQC topology, sheaf of groups. So this is G underlined is a sheaf of groups on schemes over S with FPQC topology. And now, given a G-torsor, Y over X over S, we define G underlying torsor in the previous stance. So let's call it, so let me call it this, denoted by X underlined. So how to define it? So I need to tell you what are sections of this should be a sheaf of sets. So if I have any scheme over S, I simply take sections of this. So morphisms from over S from Y to X. So if you have a scheme with an action of G, you can assign to it the sheaf of sections. Yeah? This is what's written here. You could, if you want to think in terms of sections, you can take this scheme X over S, you pull it back to Y, and then you take sections. That's the same. So now X, by the result that Katja mentioned, that any scheme, the presheaf represented by a scheme is always a sheaf. This is a sheaf of sets in FPQC topology. Ну, мы в прошлый раз доказали, что это верно, если X афинная схема. Я не доказал, я сформулировал это в общем случае, но не доказал. А давайте посмотрим, почему это верно, если X афинная схема. Ну пусть сначала X это вообще А1. Тогда, значит, что такое отображение из Y в А1? Это просто функция на Y. Значит, вот в частности утверждается, что предпучок, который каждому y сопоставляет множество функций, группу функций, глобальных функций на y, это пучок в плоской топологии. Ну, формально из плоского спуска для квазикогерентных пучков следует, что даже любой квазикогерентный пучок является пучком в плоской топологии. Вот. Поэтому, значит, если x это А1, то все следует из этого. Также если это А2, потому что это две функции. Ну а если это вообще афинное многообразие, ну что такое задать отображение в афинное многообразие? Ну это то же самое, что задать набор функций на y, удовлетворяющий некоторой системе уравнений. Ну то есть задать отображение из глобальных функций на x в глобальные функции на y. Вот. Ну, набор функций, если у вас есть плоское покрытие, то набор функций функции можно спускать. Они образуют пучок. Но если они удовлетворяли уравнением, какой-то системе уравнений на покрытии, то они будут удовлетворять и внизу. Ну вот поэтому, потому что спускать можно единственным образом. Вот. Хорошо. And now returning to the question that Stepan asked. So here is the and also Lisa. So here is the statement. So preposition. Assume that G is affine. Then sort of geometric G-torsors is the same as G underlying torsors. Okay. So what we want to prove here. So you see, so geometric G-torsor is determined by a functor from schemes over by this X over S is determined by a functor it represents. So now what we are given a functor, and we want to construct the scheme it represents. So we want to go in the opposite direction. And this requires some some work. So how we can do this? So proof. So let's construct a functor in this direction. So we have t, and we have action of g underlined on t. So the idea is the following. So locally, t is trivial. So if I have a trivial torsor, then the underlying geometric torsor will be just g that maps to S. Right? So if for trivial torsor, it's OK. So, but then, so I pick a cover of X of S where my torsor is trivial. So in each open set in this cover, I get this geometric torsor, and then I want to glue them. And we will glue them using faithfully flat descent. Okay, so I have a functor, let's say, from here to here. And so proof. So first of all, by Yoneda lemma, this is fully faithful. Fully faithful. So the key point is essential surjectivity. So I need to show that every algebraic torsor comes from this. So pick. So I have t, I have g t to t. So pick cover and sieve. Sieve u such that t restricted to u is trivial. Trivial means that it's isomorphic to g for any u in object of u. Okay? So so t over u comes well. It's in the image of this map. Determines a geometric torsor. G torsor. Okay, so let's say t. Let me maybe sorry, I think I better let me maybe let me change my notations. I'm so oh no, it's okay. It's okay. So let's say that this is geometric. So, well, it's isomorphic to U times G, but non-canonically. U times G over X. So, okay, so I have this map. And now this is a geometric torsor. And now let's call this map FU.
Shouldn't the project be over S?
Over S, thank you. So set AU be the direct image of the structure sheaf. So the key point here is that this morphism is affine because it's isomorphic to the projection from U to times G to U. And G is affine by assumption. So this morphism is affine. So given an affine scheme over U is the same as given a quasi-coherent sheaf of algebras on U, right? Just the direct image of the structure sheaf. There is a relative spectrum construction. So now I claim that this construction determines this this U goes to runs over all objects of this covariant sheaf, gives me is an algebra object in the category of quasi-coherent sheaves, locally given quasi-coherent sheaves, right? So it's therefore it defines an algebra object A in quasi-coherent sheaves on X by faithfully flat descent. On S. And now I take X to be the relative spectrum of A. Okay, so I think I have to stop here. So questions?
Does this result fail for, like, for example, for abelian schemes, or does it fail only for very, very horrible groups?
Well, I believe that it's true for group schemes which are quasi-projective. So it's definitely it would be hard to come with a counterexample. So what we proved along the way is that you can descend affine schemes along faithfully flat covers, which means that so if you have say X and a faithfully flat cover Y, FPQC cover, and you have an affine scheme Z over Y, together with a isomorphism of the two base change. So you can take Z, this is Z over Y, and you can pull it back with respect to the first projection. This is over X, and you can take the fiber product with respect to the first projection, and also with respect to the second projection. Y over X, and this is X P2. So you get two schemes over Y times Y, and suppose given Z over Y together with a descent datum, which is an isomorphism that satisfies the co-cycle condition on Y times Y times Y. Then it's this Z descends to X. So you can construct a scheme X, a scheme over X such that the Z is a pullback along this morphism. And the argument is essentially written down. So you think of Z as a sheaf of algebras on Y, quasi-coherent sheaf of algebras. And so this descent structure gives you, makes this sheaf of algebras enter an algebra object here, and then you get an algebra object in the category of quasi-coherent sheaves on X, which gives you a scheme. Okay.
I still want to elaborate on my earlier questions. In this text project and somewhere in literature, when they discuss descent, they still find it useful sometimes to work in the larger category of algebraic spaces. They have to allow just forcefully to glue schemes in the étale topology. So I want to ask, but the whole theory we're discussing works for the FPQC topology. So I want to ask, is there a reason not to glue schemes in this very big FPQC topology? Will we get something interesting, or will we get something like very postological if we try to forcefully do this?
Sorry, I kind of I don't really understand your question. So one reason why you want to introduce this algebraic spaces, so in general descent for schemes does not work, even for finite étale covers. So if this is a finite étale morphism, even with say Galois group G, and then you are given a scheme Z over Y with an action of the Galois group that covers this action here, then in general it's not possible to descend it to X. If it's possible, the descent is unique, but it need not exist. But it exists in the category of algebraic spaces.
So for algebraic spaces, étale descent for algebraic spaces works by definition.
Yes.
But, so
for FPQC descent, I don't think so.
Yeah, so, but then we could probably introduce some more
Larger category.
Yeah,
Right.
So,
Right.
is this useful, or is this pathological, or is this?
So this will be kind of a subcategory of stacks where points have no automorphisms, right?
Well, I guess.
Yes. So inside stacks, you have functors from affine schemes to groupoids, which are actually sets, have no non-trivial.
Потому что это есть схема, нет?
Нет, не любой FPQC пучок, который во множество представим.
Функторы из афинных схем множества, которые FPQC локально представим. Это будет больше, чем алгебраических пространств. Или это будет тоже самое? Ну как? известно по этому?
Не знаю, не знаю.